So I was looking a lot for, did you follow instructions with the views and the things that were asked for to be provided in each view? There were very specific instructions, and I was kind of picky about that. And then also properly modeling the truss. So that's, again, something that is tied to changing some of the default settings, right? Remember, for a truss, you have to change all of the members from rigid connect, which is the default setting, to simple connect. And that makes sure that we're modeling the truss as axial force only members that are pin connected to each other. But in order to make that model stable, after you make that change, you also have to restrain all of the nodes against rotation about Z. Otherwise, you'll get an unstable structure. And if you forget to do both of those things, then you're basically modeling that truss as a frame, which is also not correct, okay? So again, good news, beams, you don't have to change any of those default settings. You can just model the beam as a two-element system to mimic what we have in our hand calculations. All right. So today we will continue with wind loads. We'll finish up the skeleton notes handout, and then I'm going to shift gears over to the PowerPoint slides, and we will be going through, once we shift over to the PowerPoint slides, that will be taking us through the environmental loads handout associated with wind loads. So we've gone through the seismic loads section. Wind loads start on page 14 of the handout. So you may want to have that handy in front of you and follow along as we go through the slides. And then that will probably take us into Wednesday's lecture. And if we have time, we'll go through an example. I did post homework 7 on Friday, so homework 7 will be due next Wednesday, the 25th. And then, let me see, I think I have the schedule handy here. Yeah, so here we are, week 9. Homework 7 due the 25th. And then the second exam is going to be Monday, the 30th. So 2 weeks from today is exam 2. Exam 2, I anticipate will cover lectures 12 through 23. So 12, let's see. Yeah, that's right. So this is where the first exam ended, lecture 11. So lecture 12 was the beginning of finite element analysis. All right, so exam 2 will cover finite element analysis, and then dead and live loads, seismic loads, and wind loads. All right, so homework 7 covers dead and live loads, seismic loads, and wind loads. It's a little bit longer, that's why I gave you a little bit more time for it. So it'll be due next Wednesday. And probably talk a little bit more about homework 7 on Wednesday after we finish talking about wind loads. All right. Any questions so far on what's coming up? Okay. All right. Let's go back to our notes here. There we go. All right, so we were talking about the nature of wind, all right, and we started talking about wind structure interaction, or how wind flows around a building. All right, so that's where we left off. We were looking at this plan view and talking about how you've got positive pressure on that windward face, and then the other surfaces on the sides of the buildings will all have negative pressures. So the side walls will experience a negative pressure, and the leeward wall will experience negative pressure. And for design purposes, we assume that those side and leeward walls have a pressure distribution that is constant with height, whereas the windward wall, we assume that it will increase with height. And so that's what we're going to look at on the next page, is the variation with respect to elevation. And then we're also going to talk about the internal pressures that you need to consider for building. All right, so first we'll stick with external pressures for a minute. And we want to make sure to remember that these pressures, whether they are external or internal, will always be acting perpendicular to the surface. All right, so they are always going to be transverse loads with respect to the surface. All right, so for our wind flowing in this direction, let's say, we're going to consider two cases, all right? Here's a steep roof and here's a shallow roof. So the steep roof, defined in the standard, is anything above or equal to 10 degrees in slope. And the shallow or flat condition is anything less than 10. All right, so for the windward side, all right, we already talked about how we simplify our windward distribution into blocks, all right? So it might look something like this. On the roof, right, if we have a steep roof, we could have positive or negative external pressures that we need to consider, right? So there are other factors that come into play there, and we would need to check for both possibilities. On the leeward side, we would only have negative pressure on the roof and also on the leeward wall. All right. And remember that this, let's see, that the block pressures on the windward wall are a practical application, right? In theory, it's going to be more like the actual wind distribution, right? The parabolic variation. Now for a shallow roof, the walls would have the same pattern as it would for a steep roof, of course, right? So the only thing that's going to change due to the slope of the roof is the pressures on the roof. In this case, you would only have negative pressures to consider on the roof. All right, so that takes care of the external pressures on the outline of the building. Now we have to think about the internal pressures. Internal pressure is something that comes from wind seepage, right? So you have windows and doors opening and closing, ventilation systems that can allow air in or out, right? Louvers. So all of those things can affect the internal pressure of a building. And it can be either a net positive internal pressure or a net negative internal pressure. So we have to consider both options for our design. And as with the external pressures, the internal pressures will always be acting perpendicular to the surface. So if we have a positive internal pressure, then we assume the pressure is positive on all surfaces. All right, so the air on the inside is pushing against every surface. And if it's negative, the air will be pulling on every surface. All right, so I'll note what I wrote. Internal pressure comes from wind seepage. Ventilation / conditioning, etc. And we have these two cases, have to consider both. So the way this is accounted for is through what we call an internal pressure coefficient. This internal pressure coefficient has 4 letters associated with it. Makes things a little more confusing at first, but we call it capital G, capital C, and then PI. All right, so this represents a single value from a table. It's not something that we calculate. All right, so that single value will be the magnitude for both the cases that you consider. All right, so positive and negative cases use the same magnitude. And that means the same magnitude in both cases and also a constant magnitude on all surfaces, right? So I'll also note constant on each surface. So then once you figure out the external pressure and the internal pressure, then for each surface, you will calculate the design net wind pressures. So this is the net pressure, and I'm going to break down the items in this equation. First of all, we'll break down the 2 terms. So this is your external pressure in the first term, and this is your internal pressure in the second term. So the net pressure always subtracts the internal pressure from the external pressure. So it's important to keep track of the signs when you do these calculations. And remember, positive always means towards the surface, negative always means away from the surface. And so that direction, right, the direction of positive pressure is going to be opposite for your external and internal pressures, right? Because if your external pressure is positive, it's like that. If your internal pressure is positive on that same wall, it's going to be in the opposite direction, right? On the leeward side, right, you're always going to have negative pressure, so it's always going to act away. So if you have positive pressure on the leeward side, you're going to have a larger net pressure. But if you have a positive pressure on the windward side, you're going to have a smaller net pressure, right? And you're never going to have a positive pressure on one inside face and a negative pressure on the other inside face, right? Because you always consider all negative or all positive for internal pressure. All right, so as promised, I'm going to break down these items. So in the external pressure calculation, we have QZ, I'm going to call that 1, capital G, that doesn't want to go away. All right. Capital G will be 2, and then CP will be 3. So QZ represents the velocity pressure in pounds per square feet. This is something that you will calculate, all right, and it varies with height. The second term, capital G, that represents the gust effect factor. So I mentioned this before when I said we account for the dynamic effect caused by turbulence using this gust effect factor, and that's how our static analysis can account for that dynamic nature of wind structure interaction. That's going to be, well, it depends on your building, right? For most buildings, that can be considered rigid. That's just going to be a single value that you can use from the standard. If your building is considered to be flexible, which will be beyond the scope of this class, so in this class we'll only have rigid buildings to consider. But if your building is flexible, then you have to calculate the gust effect factor, all right? But that's beyond this course. And then the third item, CP, that is an external pressure coefficient. So that will depend on which wall you are calculating pressures for, and we'll look at that when we get into the tables. Now to break down the internal pressure calculation, we have two values that are multiplied together to get your internal pressure. One is QH, I'm going to call that 4, and then we have that internal pressure coefficient, all right, which is all representing one single value. I'll call that 5. All right, so QH is simply QZ evaluated at Z equals H. And this sketch right here shows you graphically, right? You've got Z as a variable distance measured from the base. H represents the mean height of the building, mean roof height. So that's noted down here. So GCPI then, I already defined that. That's something that you will obtain from a table. And I'll note above, right, the CP is also from a table. So it's a common mistake to think that you have to use the gust effect factor in both terms, right? And it's easy to see why. They look very similar to each other. But just please remember that in the internal pressure calculation, that capital G is not the gust effect factor. It's built into the internal pressure coefficient, right? So you do not use the gust effect factor for the internal pressure, only for the external pressure. So at the top of the next page, we have the equations for calculating QZ and QH, all right, the velocity pressure. The only difference between the two are the coefficients, which we will define in a moment, all right, the KZ and KZT. Those two coefficients can vary with height. KH and KHT are simply those two coefficients taken at mean roof height, right? So now we'll define all the items in this equation. First up, we've got the V, right, capital V, which represents the velocity at the mean wind velocity, right? And that is based on the location and the risk category. And you always plug that value into this equation in miles per hour. There is another version of these equations for metric, right, where you would use meters per second for V. It just has a different coefficient out front. KE represents the ground elevation factor. So this is something that is based on location, of course, right? Your elevation depends on your location. And it accounts for the fact that air density will change with elevation, right? So at higher elevations, you have a lower air density, and that helps us because a lower air density will result in being able to design for lower wind forces, lower wind pressures. And then these KZ and KZT values, first up, we'll do the KZ, KH, all right? So I'm gonna circle those up above here. All right, so KZ, QZ vary with height. All right, and technically the KZT also varies with height. Or it can, it doesn't necessarily. And then QH, KH, KHT, right? These are just the Z versions evaluated at Z equals H. All right, so these exposure coefficients, KZ and KH, these are based on the height of the building which you're calculating pressure for on the windward side. And they're also based on what's called exposure category. Exposure category depends on your location, and we'll talk about that later when we get to the slides. Then the KHT and KZT, those are topographic factors. So these will account for the shape of the terrain surrounding your building. If your building is at the base of a hill or at the top of the hill, that's going to impact how the wind will interact with it, right? Or if you're near a cliff or another, they call those escarpments, stuff like that, right? That will impact how the wind will behave approaching your building. There's a speed up factor, right? So you probably have experienced this hiking. If you get to the top of a hill or a ridge on a mountain, you know, the wind really picks up and sweeps over that ridge. So we have to think about that as well for our buildings. In this class, all right, we're going to keep it simple with the topography. We're just going to assume flat topography for our calculations. So that means we get to just use 1 for this factor. All right, and then last but not least, we have KD, the directionality factor. This is based on the geometry of the building, right? Specifically the cross-sectional shape. If it's a rectangle or a circle or something else, that's going to impact how the air will flow around it. So some shapes are more aerodynamic than others. And for most buildings, right, KD is going to be 0.5. Actually, for 4 buildings, or most buildings. I guess there are some unusual circumstances, but in the code it says buildings use KD as 0.85. So this, as I said, it's based on geometry. Specifically the plan shape. And what it does is it accounts for the fact that the design wind speed, all right, so the big event that you're designing for, it accounts for the fact that that design level event is not 100% likely to align with the worst case direction for building response, right? All right, so now we'll do a little recap. So thinking about all the factors that influence wind loads, right? Wind loads are kind of tedious. There's a lot of factors to keep track of, a lot of things to calculate, a lot of things to tabulate. But if we break it down to just a handful of important features or characteristics of your building, what can we boil it down to that really influences the wind loads? What's
Location.
one? Yeah, location. That's a big one.
Height of the building.
Yep, the height of the building. Also going to wrap into that the other dimensions of the building, so we'll just call it building geometry. Those are the two biggest ones. Can anyone think of other things we've talked about that are related to the building that affect some of these factors? Yep.
Your internal pressures.
Yep. So what are the internal pressures? What feature of the building can be tied to internal pressures? Yeah, so building openings, things like that. Yep. Did you have one back there?
Oh, I was gonna say conditioning.
Conditioning, yeah. So all of that, yeah, and that's all related to how many openings or, how open or enclosed your building is. All right, and there's one more, and it's another thing, so similar to location, that is crucial for all environmental loads.
Maybe topography, maybe?
So that would be built into the location of the building. So we kind of have that covered.
The strength of the events that occur there?
Magnitude of the events, yep. So that would also, I would associate that with location as well. So think of something that is tied to the actual building rather than the events or location surrounding it. Something that doesn't fall under geometry or openings, but is directly tied to the building.
Materials?
Not quite. So that is something that would affect seismic loads for sure, right? But not necessarily, not wind loads. At least not with this method. So if you're thinking of the cladding and stuff, that would kind of fall under how enclosed the building is. So that would kind of fall under openings. So it's not something that's actually structural. It's really more of associated with what's the purpose of the building.
The risk factor?
Yeah, the risk category, right, which is tied to the building's use. All right, so if we think about all the items that are dependent on these four things, for location, right, you have exposure, that's KZ, elevation, which is KE, topography, that's your KZT, and wind speed. All right, and the factors that depend on building geometry. that would be your KZ, right? KZ varies with height. Your KZT, we didn't talk about those details yet, but that one also can vary with height. KD, right, that's based on the shape of the building in plan. And then we haven't talked about these yet specifically, but your external wall coefficient, which we defined in the previous equation, and the gust effect factor all technically are tied to the geometry of the building. We'll look at the wall pressure coefficient later in more detail. Openings, right, that's directly tied to your internal pressure coefficient, GCPI. And the use of the building, that comes into play through the wind speed. So we'll see that next when we start going through the slides. All right, so specifically, the wind speed that you use is going to depend on the risk category of your building as well as the location. So since we have 4 different risk categories, there are going to be 4 different maps for wind speed. All right. Any questions so far? All right, so before we switch over to the PowerPoint, I'm going to show you a few images here that I've got. So this is what I mentioned the other day, right? This was the microburst, which was technically a downburst that occurred in the Tobacco Root Mountains several years ago. I think this was in August 2019. Flattened trees over 200 to 250 acres in that range. And so you can see, right, just how powerful those downbursts can be from that. Let's see. A few other wind-related images here too. So this was from the 1990s, right? In 92, Hurricane Andrew really just devastated parts of Florida. And Florida wasn't the only state that was affected by this, but one of the unique things about this hurricane in particular is the number and intensity of tornadoes that it spawned. So a lot of hurricanes, most of the damage from those hurricanes will come from storm surge. That was the case with Hurricane Katrina. But this one was a little bit unusual in that most of the damage actually came from wind and specifically tornadoes that were spawned by the hurricane. So you can see like there are just entire blocks that were destroyed. And so that's one unique thing about tornadoes is they can be very site specific. So some neighborhoods you'll see where there are, one house is totally destroyed and another house is intact and then another house is totally destroyed. And some of that can have to do also with how well those houses are connected together, right? Of particular importance is the connection between the roof and the walls and then the walls and the foundation. So if they're not tied down properly, those elements can just be ripped off by strong winds. And this hurricane in particular, because of the damage that it caused through those tornadoes, that triggered code changes. So after this hurricane, they started requiring that roofs be tied down to walls and walls be tied down to foundations with specific, level of minimum strength. So after the mid-1990s, right, any new construction should have those requirements met. But if you're ever, in the market for a house and it was built before the mid-1990s, you just might want to verify that it's properly tied down and tied together to resist against uplift. So, yeah. So anyway, a little bit of interesting history for you there. All right. So, and then for comparison, right? So here's some of the damage that occurred due to Hurricane Katrina, right, which was significant storm surge. So the storm surge was able to just like lift structures up off of their foundations and carry them certain distances and then deposit them wherever they landed, right? So there were cases of entire casinos being relocated, and that was pretty significant. So I've got a few notes in here. Yeah. So Hurricane Katrina also triggered some new regulations in certain areas as well. There are some towns that still have not recovered. They were essentially abandoned after Hurricane Katrina. But here's some more damage from Hurricane Katrina. You can see, I don't know where this building came from, but it definitely wasn't there to begin with, right? So yeah, pretty significant damage can come from these events, as we all know. But since it's relevant to the topic, I figured I'd throw in a few pictures. All right, so let me switch over to the PowerPoint here. And there we go, wind loads. All right. Oh, let me switch back up here too. There we go. All right. All right, so I invite you to follow along in the ASCE 7 handout, starting on page 14. First, I think I have this page on there. Yep. So page 14 should look something like this for you. This outlines all of the chapters, right? So it's just kind of showing you the organization of all the wind load related chapters in ASCE 7. So chapter 26 covers all of the basic criteria that applies to all of the methods. There are several different methods that we can use to evaluate wind loads. In this class, we're going to be focusing on the main wind force resisting system, specifically chapter 27, the directional procedure for buildings of all types. But as you can see, there's several other options for the main wind force resisting system analysis. And for components and cladding, there are also several options there. Most of them are covered in chapter 30. Chapter 31 covers the wind tunnel procedure for both types of analyses. So that's something that we would apply to a tall building in an urban area, for example. But again, in this class, we'll be focusing on chapter 26 and then chapter 27. So first up, these mapped wind speeds. The one that I'm showing you here is the second one of the four, right? So it's B, figure B of 26.5-1. And this one is specific to risk category 2 structures. So you can see it's similar to the seismic maps with contours, except that it's a lot easier to read because they're not as condensed as they were in the seismic loads maps. So unlike the seismic loads, right, you can actually use these paper maps to read your wind speed if you want to. But we also have that handy AT Council tool that can give you a more specific value if you're in between contours and you don't feel like interpolating or being conservative, right? So normally you wouldn't try too hard to get an exact interpolation. You would just kind of lean towards the conservative reading. All right, so that pop-up shows the other risk categories, which maps they're associated with. All four are included in your handout. And then if you see a shaded area, All right, that means that you have a special wind region, and so you're not going to have a value from the map for that wind region. That means you just have to get your wind speed from the authority having jurisdiction, right? So your local authority. Regardless of whether you have a shaded region or not, though, you should still always consult your local authority to make sure that they don't have anything higher that they require, right? So in the notes at the bottom of these maps, the last one says you can also go to this atcouncil.org website to find your wind speed. So if we were to consider Bozeman, for example, the Bozeman city criteria lists wind speeds of, there's two options, all right? So they list the 3-second gust wind speed of 90 miles per hour, and they list the fastest first mile wind speed of 75 miles per hour. Now that stuff is from old versions of the code, all right, old versions of the standard. It's pretty outdated. It would be a better idea to just use the higher values that you would obtain from the wind speed map. So if we look at the map, right, for risk category 2, you can see that most of Montana is between 105 and 110 miles per hour, right? And certainly Bozeman is between those values. So you can see that the new version of the standard has a higher minimum recommendation than what the city currently calls for, even though the city cites the building code of Montana, which cites the current version of ASC 7, which has the higher wind speeds. So they just haven't updated this document, really, is what it comes down to. All right, so moving on then. The directionality factor, this you can find on page 23 of your handout. And at the very top, you can see where it says 0.85 for buildings. And then you can see the other options below, right? So like chimneys and things would have a higher directionality factor and so on. All right, then KZ, right? This one's a little bit more involved, right? Requires a little bit more effort to figure out. We enter this table using the height above the ground, right? Which is going to be variable for your windward wall. And also with the exposure category, which we haven't yet defined. Now, one thing that I meant to mention back on the maps, all right, so here, did I put a note on there? No, I didn't. Okay, so one thing you'll notice on these maps when you read them is that you have a value and then a value in parentheses. The value in parentheses is just the metric version, all right? So you've got miles per hour and then meters per second in parentheses. So that's pretty standard throughout the standard. Wherever you see values in parentheses, it's just the metric equivalent. So you can ignore that for this class. And so that's similar in this table as well. I've crossed out the metric versions for KZ, but we want to enter with height in feet and then exposure category. So now we'll talk about exposure category. So this is something where it's another A, B, C, D option, right? We don't go through E and F, but A through D. Or not A anymore. There used to be an A. So just B, C, and D. So these three refer to surface roughness categories, right? Outlined in this section. The surface roughness categories are defined here, all right? So this is based on the surrounding terrain. And basically what it comes down to is category B represents urban and suburban areas, wooded areas, things that have a lot of closely spaced obstructions. C represents open terrain with scattered obstructions, right? For example, grasslands. And then category D would represent a flat, unobstructed surface like water, open water, smooth mud flats, unbroken ice, things like that. So in this class, you won't have to worry about reading through all this text and figuring out which exposure category you have, because it can be very specific, right, as far as distances of each of these terrain, surface roughness categories, and things like that. In this class, I will just describe to you something like this, or something like this, or something like this. And then you just need to know which letter to choose, and that will be your exposure category. So this is a little bit more information. You don't need to know it for this class, but just for context, this is how detailed and specific those definitions can get, right? And then here are some examples that are provided in ASCE 7 for each exposure category. So this would be a suburban area, right, with mostly single-family dwellings. This is more of an urban area with numerous closely spaced obstructions having single-family dwelling size or higher. There used to be a category A, as I mentioned before. What do you think that was?
Specifically for cities.
Yeah, it was. It was specifically for cities, like urban downtown areas. But now we use wind tunnel studies for things like that. So they abandoned exposure category A, and now we use exposure B. So the way that these exposure categories work, right, for wind loads, exposure B would be the best case scenario because it provides more protection from the wind. Exposure D would be the worst because it's just a flat surface, right? You're completely open to whatever the wind is gonna blast you with. So exposure category A was a little bit too good to be true for urban areas, which is why they ditched it and started just doing wind tunnel studies instead. Or if you don't do a wind tunnel study, you would use exposure B for an urban area. Here's an example of exposure C, right? Flat open grassland. I know we're almost out of time, right? More C, that would be D. And Bozeman says exposure C, right? So even though it's arguable that there are certain areas of Bozeman that would probably fit exposure B, right? But it's conservative to use exposure C. That's the worst case. So even if you're in an area that fits more of the suburban description in Bozeman, the city requires you to use exposure C instead, right? All right, so we'll stop there, pick up with the rest of this on Wednesday, and I will see you then.